Welcome back to the course Rocket Propulsion offered by EDAL Systems. In today's class, we will discuss about solid propellant rocket engines. So the index for the today's class is, first we will discuss the background of solid propellant rocket engines. That is, we will cover the process, the components which are present in solid propellant rocket engines, various applications, various advantages, disadvantages of using these kind of rocket engines, then the broad classification based on various factors. Then we will move on to the second topic, that is different types of solid propellants, in which we will see a broad classification of solid propellants based on various factors. Then we will see each of the propellants in detail with their examples. Then we will cover the desirable physical properties of the solid propellants which are needed in solid propellant rocket engines. Then we will see different hazards which are included with the propellant. So each propellant have its own set of hazards. We will discuss them and we will see what all remedies we can provide so that we can avoid such hazards while using the propellant. Then again we will see some solid propellant ingredients. So along with the fuel and oxidizer, which are several ingredients which are used when we manufacture a solid propellant rocket engine. Then we will move on to the third topic, that is propellant grain and grain configurations. So what is a propellant grain and what are the various grain configurations which were used previously and which are used even today? We will discuss this in brief. Then we will see the complex combustion process which is involved with solid propellant rocket engines and why a thrust termination is necessary in solid propellant rocket engines and how we can attain that with some certain processes. So we will discuss even that. Then the fifth topic, that is combustion instabilities. So this is a very complex kind of combustion. So instabilities will be part of it, but we will see what are different kinds of instabilities for solid propellant rocket engines and how we can assist them, and we can provide some remedies using some design challenges, etc. Then we will see how analysis and simulation help us to gain more knowledge to inspect for this instability and provide remedies. Then lastly, we will see propellant processing and manufacture. So how these solid propellants have been processed and how they are manufactured based on their classifications, we will discuss in detail. So let's start. So we'll start with background of solid propellant rocket engines. So we have seen that solid propellant rocket engine is a very simple when we compare it with liquid propellant rocket engines, because the propellant is contained and stored directly into the combustion chamber, and sometimes it is sealed in the chamber for long time storage. That is, it can be stored for around 5 to 20 years into the combustion chamber itself for a solid propellant rocket engine. But we have seen for liquid propellants, we have to store them into different tanks and then we have to maintain them at some certain pressure for a short duration. The motors come in many different types and sizes, varying in thrust from about 2 Newton to over 12 million Newton. So the solid motors, they come into different sizes, into different types, and based on various thrust levels between 2 Newton to around 12 million Newton. So they have no moving parts, as we have discussed that it is a very simple design with no moving parts. It just has an igniter, the grain, propellant grain, which is stored inside the combustion chamber, and some of the control valves or flanges, perforations, etc. are present. But some motor designs include movable nozzles and actuators for vectoring the line of thrust relative to the motor axis. So we can achieve this thrust vectoring, or we can say modifying the thrust using the thrust vector control devices which are present. So to achieve that, there are some other devices which are included with the solid motor rocket engine design. The solid propellant charge is called the grain and it contains all the chemical elements for complete burning. So earlier we have seen that liquid propellants, they have different fuel and different oxidizer which are stored separately. But for solid propellants, the fuel and oxidizer, it contain within a one single solid material which is called as propellant grain and which is stored and sealed inside the combustion chamber for long years. So once it is ignited, it usually burns smoothly at a predetermined rate on all exposed internal surfaces of the grain. So the igniter is placed, we just have to ignite the solid propellant grain and the internal surfaces of the grain will start burning, and it will burn at a predetermined rate which has been calculated, and then the exhaust gases will move towards the nozzle and there they will be expanded and thus the thrust will be generated. So when we compare the solid propellants with liquid rockets, the solid propellants are usually relatively simple and are easy to apply. That is, they often constitute most of the vehicle structure and require little servicing. Because there are no moving parts, there are no tanks and different pump systems to store and maintain or control the pressure inside the tanks. The solid propellant is relatively very simple and easy to operate and requires little service. But again, they cannot be fully checked out prior to use, and thrust cannot usually be randomly varied in flight. So these are some of the difficulties which are aligned with solid propellant rocket engines. Now we'll see some of the advantages and disadvantages of solid propellant rocket engines. So first one that we have seen, it is very simple design because there are no moving parts and it is easy to operate. There are little pre-flight checkouts available for solid propellants. Then it is ready to operate quickly. It will not leak, spill or slosh, and sometimes the less overall weight for low total impulse applications. So with less overall weight, we can use it for low total impulse application, which is good because for a small application, if we are using a liquid propellant rocket engine, then the design become very complex and many things may go wrong if one single component acts differently. That can be stored for around 10 to 30 years, and usually high overall density allows more compact package, smaller vehicle design, which will give us less drag, and can be designed for recovery, refurbishing, and reuse. So some space shuttle solid rocket motors are used for recovery, refurbishing, and for reuse also. The thrust termination devices permit control over total impulse. So if we want to control the total impulse, there are some certain thrust termination devices which will allow us to do so. Then the disadvantages for solid propellant rocket engines are that many require environmental permit and safety features for transport on public conveyances. Because we carry such explosive chemical fuel and oxidizer with us which is contained into the grain, so they are very harmful for environment. Explosion and fire potential is larger, failure can be catastrophic. Most cannot accept bullet impact or being dropped onto a hard surface. The elements which compose the propellant grain are explosive and the failure can be very catastrophic. Then it requires a different ignition system. Exhaust gases are usually toxic for composite propellants containing ammonium perchlorate. So the propellants which include ammonium perchlorate into it as their fuel or oxidizer, so the exhaust gases are very toxic. Then only some motors can be stopped at random, but motor becomes visible, that is not reusable. So even if we are able to stop the solid propellant rocket motor which is burning, then we won't be able to use the same rocket motor again because it will be disabled and we won't be able to use it again. Then once ignited cannot change predetermined thrust or duration. Yeah, once the solid grain has been ignited, we cannot change the predetermined thrust or the duration which is pre-analyzed. Then we will see the process of solid propellant rocket engine, that how it works. So the grain is the solid body of the hardened propellant and typically accounts for 82 to 94% of the total motor. So the propellant grain, which is the charge which will burn and which will produce the thrust, it accounts for almost 80 to 94% of the motor total mass. So to start the process, the igniter is used which is electrically activated, which will provide the energy to start the combustion. Once the igniter has activated, the grain starts to burn on its exposed inner surfaces. The igniter is placed inside the grain cavity. So once it has been ignited, the exposed inner surfaces which are close to the igniter, they will start burning. Then the hot reaction gases flow along the perforation or port cavity toward the nozzle. So most of the propellants, they have cavity between the propellant grain where at the start of the grain the igniter is placed, and once it starts burning, the hot reaction gases, they will flow along the direction of the perforation and then they will move towards the nozzle. So the inner surfaces of the case, which is really a pressure vessel, which are exposed directly to the hot gases, have a thermal protection. But we can say it has an insulation layer to keep the case from becoming too hot, in which case it would not longer carry its pressure and other loads. So this is very useful because the hot gases which are produced, it may increase the chamber pressure in very high magnitude such that the material will be stressed a lot and it may even cause a catastrophic failure. Then the next part, that is the nozzle, accelerates these hot gases which is made of high temperature materials. The combustion chamber in which these hot gases or in which the solid propellant grain is stored has to be made of very strong materials, and then even the nozzle has to be made to withstand high temperature stresses. So for this nozzle, usually a graphite and or an ablative material to absorb the heat is used to withstand such high temperatures and the erosion. So in the figure we can see complete components are given for solid propellant rocket engine. So we can see an igniter is placed at first inside the case, and then there is a cavity for this propellant grain which is with the dashed line we can see, and there is a mounting flange which is used to mount this rocket motor with the space shuttle or with the spacecraft which we are using. Then we have an insulation layer for this case. Then a nozzle is attached to this combustion chamber. So each motor is fastened to its vehicle by a thrust carrying structure. So in figure we can see that there is a skirt with a flange integral with the case which is fastened to the vehicle. So this is the complete component diagram for a solid propellant rocket engine. And as we have discussed that there is no active cooling and the motor must be designed to withstand the transient heat loads without failure. So the material which is used to make this case, it is mostly used of titanium or some alloy metals. Moving on to the next part, we will discuss about applications of solid propellant rocket engine. So first, that is, it is used for large boosters and second stage motors, such like space launch vehicles or lower stage of long range ballistical missiles. Then it may be used for ballistic missile defenses, that is, defense against long and medium range ballistic missiles. Again, can be used for high altitude motors, such as upper stages of multi-stage ballistic missiles, space launch vehicles, or space maneuvers. Then can be used as a propellant for gas generators, which will be useful for pilot emergency escape or push missiles from submarine launch tubes or land mobile canisters. It can also be used for some actuators and valves, which will give short-term power supply, jet engine starter, munition dispersion, rocket turbine drive starter, automotive, or airbags. So these are the various applications which come under gas generator. So these are the very small applications compared to what we use for our rocket engine boosters. Then it can be used for some tactical missiles where high acceleration is needed, that is short range bombardment and anti-tank missiles are used, and can be also used for modest acceleration, that is guided or unguided, or air to surface, surface to air, short range guided surface to surface, and air to air missiles. Again, under tactical missiles, it can be for infantry support weapons, shoulder fired anti tank or anti aircraft missiles or motors. So, these are various applications of solid propellant rocket engines, which mostly include the defense part, because as we have seen, the features of solid propellants is that once it has ignited, it will burn at a predetermined rate, and the extinction or the termination of the thrust is very difficult in solid propellant rocket engines. So that once it is fired, it will completely burn the grain and then it will stop. So now we will see the classification of solid propellant rocket engines. So there are again various factors based on which this classification of solid propellant rocket engines can be done. So some of them we will discuss now. That is, first is propellant. So based on propellants, we can classify them as composite, double base, or composite modified double base propellants. So for composite propellants, it is a heterogeneous mixture of powdered metal, that is, powdered metal, it may be a fuel, then the crystalline oxidizer and polymer binder. Then for double base propellants, it is a homogeneous mixture of two explosives, usually nitroglycerine or nitrocellulose, and the last one, that is composite modified double base propellants, which is combination of composite and double base ingredients. Then the next category of classification is the case design. So the combustion chamber, based on the design of the case, the solid propellant rocket engines can be classified into three categories, that is steel monolithic, fiber monolithic, or segmented. So the steel monolithic, it is a one-piece steel case. So the entire structure, it is made of steel. Then for fiber monolithic, filament mount with plastic matrix is used to manufacture the fiber monolithic case design. For segmented, the case and grain are in segments which are transported separately and fastened together at launch site. The segmented is mostly made of steel, and they are made in separate parts which are then transported separately and fastened together at the launch site. Then the third category based on which the solid propellant rocket engines can be classified is the grain installation. So it may be case bonded or cartridge loaded. So in case bonded grain installation design, the adhesion exists between grain and case or between grain and insulation and case, The propellant is usually cast into the case. So in case bonded, generally the combustion chamber into which the grain has to be stored. The case itself becomes the mold in which the solid propellants are then poured and they are allowed to cure, while for cartridge loaded, the grain is formed separately from the motor case and then assembled into the case. So there's are two ways how we can make this grain associated with the case. Then there are other categories, that is the explosive hazard, grain configuration, diameter or length, then exhaust gases, and based on the thrust action. So based on the explosive hazard, we can classify the solid propellant rocket engines as class 1.3 or class 1.1. That is class 1.3 will say catastrophic failure shows evidence of burning and explosion, that is no detonation. So class 1.3 includes non-detonable solid propellant rockets. Then class 1.1 will describe catastrophic failure, which will show us the evidence of detonation. So class 1.1 is the hazardous because catastrophe can occur because of the detonation. And class 1.3 is little mild than class 1.1. So based on the grain configuration, we can classify it as cylindrical or end burning. So cylindrical shaped, usually hollow. So the cylindrical shaped grain is having a cavity or a slot in between, and the end burning is a solid cylinder propellant grain. It is a complete grain. There is no perforation given. Then based on the diameter and length, solid propellant rocket engines can be classified as with the diameter of around 0.005 meter to 6.6 meter or 0.025 meter to 45 meter of diameter. Then based on exhaust gases, we can classify them as toxic and non-toxic. Most of the exhaust gases which are produced after using these chemicals is toxic, but there are some developments which are made which have showed that the exhaust gases which are produced by using the solid propellants will give us non-toxic gases. So based on the thrust action, we can classify solid propellant rocket engines as neutral grain, progressive grain, regressive, pulse rocket, or step thrust rocket. So in the neutral grain, the thrust remains essentially constant during the burn period. So as the grain burns, the thrust will remain constant along with the time. In the progressive grain, the thrust will increase along with the time, and in regressive it will be opposite, that the thrust will decrease along with the time. In the pulse rocket, two or more independent thrust pulses or burning periods are available, while in the step thrust rocket, usually two distinct levels of thrust are available. So this is the broad classification of solid propellant rocket engines based on several factors, and the several categories are being made. But the most widely used category which we follow is based on the propellants. So based on the three types of propellants, we can classify the solid propellant rocket engines, which we will see next. So the types of solid propellants. So we'll see the classification first, that is processed modern propellants can be classified in several ways. This classification is not rigorous or complete. Sometimes the same propellant will fit into two or more of the classification. So earlier we have seen classification of solid propellant rocket engines. Now under which we have seen based on the propellants we can classify them. So we'll see different solid propellants and its classification. That is, first we will see specific application based, that is space launch booster propellants or tactical missile propellants. So based on the applications where they are used, we can classify them, or based on the density of the smoke in the exhaust plume, we can classify them as smoky, reduced smoke, or minimum smoke, which we can essentially say that it is smokeless. Then again, double base propellants, that is, they form a homogeneous propellant grain, usually a nitrocellulose, a solid ingredient which absorbs liquid nitroglycerine plus minor percentage of additive. So this double base propellants, they form a homogeneous propellant grain including nitroglycerine and nitrocellulose. Then based on safety ratings for detonation, they can be classified as detonable material or non-detonable material. Then composite propellants, we have seen that they form heterogeneous propellant grain with the oxidizer crystals and a powdered fuel, usually aluminium, held together in a matrix of synthetic rubber or plastic binder such as polybutadiene, which is also called as HTPP. Then the next class based on some of the principal manufacturing processes used, that is either the propellant is cast propellant or extruded propellant. So how the grain has been manufactured, based on that we can classify them. Then we have toxicity of the exhaust gases, that is toxic and non-toxic propellant. Then the next one, that is based on the principal ingredient, that is principal oxidizer or the principal binder or fueling. Then the last one, that is experimental or production propellants. So this is how we can classify the solid propellants based on several factors, and now we will see each of them in more detail. So based on specific applications, we have some solid propellants which are used for space launch boosters or tactical missiles, where each of them has somewhat specific chemical ingredients, different burning rates, different physical properties, and different performances. This is true because the application varies from small tactical missiles to huge space launch vehicles. Then the next category, that is based on the density of the smoke in the exhaust plume, they can be classified as smoky, reduced smoke, or minimum smoke, essentially smokeless. So the aluminium powder which is used as a desirable fuel ingredient is oxidized to aluminium oxide, which forms visible small solid smoke particles in the exhaust gas. So the aluminium powder, which is generally used as a fuel in some of the propellants, when it is burned, it is oxidized to aluminium oxide. Thus, it will form some small solid smoke particles in the exhaust gas. So it will make the smoky propellant. So most composite propellants are smoky. But by reducing the aluminium content in composite propellant, the amount of smoke can also be reduced. Carbon or soot particles and metal oxides such as zirconium oxide or iron oxide can also be visible if in high enough concentrations is used. So if we replace this aluminium powder to other chemicals such as zirconium oxide or even iron oxide in large quantities, then the smoke will be produced. So it is very difficult to attain to some non-smoky chemical solid propellants. Then the next category, that is based on the safety ratings for detonation, that is earlier we have seen, that is class 1.1, which will be for detonable material, and class 1.3 for non-detonable material. So the examples of class 1.1 propellant are number of double base propellants and composite propellants containing a significant portion of solid explosives, example HMX or RDX, together with certain other ingredients. So when we use some solid explosives such as HMX or RDX, then this kind of propellants will become hazardous and they might come into the class of 1.1 or class 1.3 category of solid propellants. Then the next classification we will see based on principle of manufacturing processes used. So we have seen that cast propellant and extruded propellant are there under this category. So cast propellant is made by mechanical mixing of solid and liquid ingredients, followed by casting and curing. It is the most common process for composite propellants. So the composite propellants mostly use this kind of casting process for the manufacture. Then curing of many cast propellants is by chemical reaction between binder and curing agent at elevated temperatures. However, there are some that can be cured at ambient temperatures also, or hardened by a non-chemical process such as crystallization. So casting is one manufacturing process through which we can manufacture composite propellants. So it becomes cast propellant. Then propellant can also be made by a solvation process, that is dissolving a plasticizer in a solid pelletized matrix whose volume is expanded. So the extruded propellant is made by mechanical mixing, that is rolling into sheets, followed by extrusion, that is pushing through a die at high pressures. So the solvation and extrusion process apply primarily to double base propellants. So these two kind of manufacturing processes are used for two different kind of propellants, that is for composites the casting process is used, and for the double base propellants the solvation and extrusion processes are used. Next category based on the principal ingredients such as the principal oxidizer, ammonium perchlorate propellants, ammonium nitrate propellants, or azide type propellants, or the principal binder or fuel ingredients such as polybutadiene propellants or aluminized propellants. So they can be classified based on the principal ingredient, which we have seen ammonium perchlorate has been used in many propellants, then polybutadiene is used in many propellants. So based on their names they can also be classified. Then the next category, that is experimental or production propellants. So the culmination of good R&D is to have a propellant selected for production in a flight vehicle application. Such propellant is selected after extensive testing, that is pre-flight test, qualification tests, and demonstrated safety, life, and other unique properties. So when we manufacture any propellant, then we have to assure that it is safe, but the propellants which are manufactured for high applications such like space launch vehicles, then we cannot test them completely. So we have to make some small batches or small samples of such exact propellant which is built for space shuttle, and then we have to test fire to check their qualities and properties. So based on that we can classify the solid propellants as experimental or production propellants. Then the category we will discuss now is the double base propellants. So we have seen that it forms a homogeneous propellant grain Usually it consists nitrocellulose, that is, it is a solid ingredient which absorbs liquid nitroglycerine plus minor percentages of additive. So in double-base propellants, the nitrocellulose is the solid ingredient and the nitroglycerine is the liquid fuel, and with the help of extrusion process, these two are combined together and a double-base propellant is formed with some minor percentages of additives. Both the ingredients which are used are explosive and function as a combined fuel and oxidizer. Both extruded double base and the cast double base propellant have found extensive applications mostly in small tactical missiles of older design. So by adding crystalline nitramines, that is HMX or RDX, the performance and density can be improved. This is sometimes then called as cast modified double base propellant. Then a further improvement is to add an elastomeric binder, that is rubber-like such as cross-linked polybutadiene, which improves the physical properties and allows more nitramine and thus improves the performance slightly. So again, for the basic or the primary nitrocellulose and nitroglycerine propellants, further some more chemicals can be added and then the performance can be improved in some areas. So further improvement is to add an elastomeric binder such as cross-linked polybutadiene, which improves the physical properties and allow more nitramine and thus improves the performance slightly. So even this resulting propellant is called as elastomeric modified case double base propellant. So these four classes or double base have nearly smokeless exhausts. So by using some of the different chemicals, we were able to reduce this exhaust smoke. Then adding some solid aluminium perchlorate and aluminium increases the density and the specific impulse slightly, but the exhaust gas is smooth. The propellant is called as composite modified double base propellant or CMDP. So along with the nitroglycerine and nitrocellulose, if we add a little of aluminium perchlorate and aluminium, then the propellant which is formed is called as composite modified double base propellant. But again, when we are using aluminium, it will give us the oxidized aluminium oxide, which will have some small solid material in its smoke. The next one we will discuss about composite propellants. So they form a heterogeneous propellant grain with the oxidizer crystals and a powdered fuel, usually aluminium, held together in a matrix of synthetic rubber or plastic binders such as polybutadiene. The crystal oxidizers and powdered fuel form this composite propellants, in which they are cast from a mix of solid and liquid ingredients, so in which solid will include the ammonium perchlorate crystals or aluminium powder, and the liquid will include HTPB or PPG, that is polybutadiene. Propellant is hardened by cross-linking or curing the liquid binder polymer with a small amount of curing agent and curing it in an oven where it becomes hard and solid. So for a certain set of chemicals, curing agent is also required to cross-link or to solidify the binder polymer. In the last 3 decades, the composite propellants have been the most commonly used class. They can be further subdivided into 5 categories. So the first one, that is conventional composite propellants, usually contain between 60 and 72% AP as crystalline oxidizer, up to 22% aluminium powder as a metal fuel, and 8 to 16% of elastomeric binder, that is organic polymer, including its plasticizer. So the first or the conventional which we have seen, which we discussed now, it will contain around 60 to 72% of ammonium perchlorate as the crystalline oxidizer and 22% of aluminium powder, which will constitute as our fuel. Then the elastomeric binder, that is 8 to 16% of its composition. Then the second category, that is modified composite propellants, where an energetic nitramine, that is HMX or RDX, is added for obtaining a little more performance and also a somewhat higher density. So using an energetic nitramine, the density can be increased and a little more performance can be obtained by adding it with the conventional propellants. Then modified composite propellants, where an energetic plasticizer such as nitroglycerine is added to give a little more performance. Sometimes HMX is also added. So the plasticizer such as nitroglycerine is used. Mostly it is used in double base propellants to modify some of the performance for the conventional composite propellant. Then the next 2 categories, that is a high energy composite solid propellant with some aluminium, where the organic elastomeric binder and plasticizer are largely replaced by energetic materials such as certain explosives, and where some of the ammonium perchlorate is replaced by HMX. Some of these are called elastomeric modified cast double base propellants, that is EMCDB, most are experimental propellants, the theoretical specific impulse can be between 270 and 275 seconds at standard conditions. And the last category, that is a low energy composite propellant, where ammonium nitrate, that is AN, is the crystalline oxidizer and no ammonium perchlorate is used. It is used mostly for gas generator propellant. If a large amount of HMX is added, it can become a minimum smoke propellant with fair performance. So here the conventional ammonium perchlorate has been replaced by ammonium nitrate as the crystal oxidizer, and this is mostly used for gas generator propellants. So by changing the composition of the chemicals present into the propellants, we can classify them and we can improve their performance, can increase some of the desirable properties of the propellants for better use for our application. So next we will see some of the desirable physical properties of solid propellants. So the first one, that is high performance or high specific impulse is needed, which really means that high gas temperature and or low gas molecular mass. So the propellant should provide high specific impulse, that is it should maintain high gas temperature and should have low gas molecular mass such that it will have high density. Then predictable, reproducible and initially adjustable burning rate to fit the need of the grain design and the thrust time requirement. It should be predictable and reproducible for the ignition process and should adjust the burning rate to fit the need of the grain design at the initial part. Then the third one, that is for minimum variation in thrust or chamber pressure, the pressure or burning rate exponent and the temperature coefficients should be small. So the burning rate exponent and the temperature coefficients should be small for minimum variation in thrust or the chamber pressure. Then adequate physical properties including bond strength over the intended operating temperature ranges should be good. It should have high density, which will allow a small volume motor. Then it should be predictable, reproducible ignition qualities such as reasonable ignition over pressure. So it should have reasonable ignition pressure to start the ignition of the solid propellants. Then desirable aging characteristics and long lives. That is, aging and life predictions depend on the propellant's chemical and physical properties. The propellant should not age early and should have a long storage life. Low absorption of moisture, which often causes chemical deterioration. Then the next set of physical properties, that is, it should be simple, reproducible, safe, low cost, controllable and low hazard manufacturing. Then there should be guaranteed availability of all raw materials and purchased components over the production and the operating life of the propellant. So there should be ample amount of supply for all raw materials and the components which are used for the production. It should be safe, it should be low cost, it should be controllable and should not have hazards when it is manufactured. Low technical risks such as favorable history of prior applications, relative insensitivity to certain energy stimuli, non-toxic and non-corrosive exhaust gases, also called as green exhaust. So you should have green exhaust which should not be harmful for the environment, not prone to combustion instability. It should not have any combustion instability with that same composition, performance and properties with every new propellant batch. So every propellant which is manufactured with the batch processes, it should have the same properties, same qualities. No slow or long-term chemical reaction or migration between propellant ingredients or between propellant and insulate. So these are the some physical desirable properties of solid propellants which are used in solid rocket motor engines. Next we will see some of the solid propellant ingredients. So the ingredient properties and impurities can have a profound effect on the propellant characteristics. A seemingly minor change in one ingredient can cause measurable changes in ballistic properties, physical properties, migration, aging, or ease of manufacture. So we have seen different ingredients which are added to the solid propellants which will enhance their performance and reduce the non-desirable properties of the propellants. So here is the list of some ingredients for composite and for double base propellants, and this list is not complete at least 200 other ingredients have been tried in experimental rocket motors. So these are some of the ingredients which are used in solid propellants. So this is not the only list, and there are still many other propellants which are being tested and which are being experimented for solid propellant rocket motors. So under double base and composite modified double base propellants, we have binder, reactive plasticizer, burn rate modifier, coolant oxidizer, stabilizer and or antioxidant, visible flame suppressant, and lubricant. So there are some ingredients which are present only for double base propellants and some are there which are only present for composite base propellants. This is because both of them are manufactured in different processes. So under composite solid propellants, we have metal fuel, which will also act as a combustion stabilizer. Then the fuel and the binder, that is polybutadiene type or polyether and polyester type. Then the curing agent or cross-linker, which reacts with the polymer binder. Then burn rate modifier, explosive filler, plasticizer for pot life control, and bonding agent. So these are certain propellant ingredients which are used in double base propellants and composite propellants. We will discuss some of them in brief. So the binders, they provide the structural glue or matrix in which solid granular ingredients are held together in a composite propellant. The raw materials are liquid prepolymers or monomers. Polyethers, polyesters, and polybutadienes have been used. So binder is mostly used in composite propellants, which will act as a glue or matrix in which the solid ingredients are held together. Then the next one, that is burning rate catalyst or burning rate modifier. It is mostly used to modify the burn rate or improve the burn rate. That is, it helps to accelerate or decelerate the combustion at the burning surface and increases or decreases the propellant burning rate. So some like iron oxidizer or lead citrate increases the burning rate. These are examples of burning rate modifier. Then we have curing agent or cross-linker. It causes the prepolymers to form longer chains of larger molecular mass and interlocks between chains. So they are used only with composite propellants and are the ingredient that causes the binder to solidify and become hard. So curing agent is only used in composite propellants which cause the binder to solidify and become hard. That is, it is mostly used to cure the binder in the composite propellants. Next we have plasticizer. So it is usually a relatively low viscosity liquid organic ingredient which is also a fuel for some of the propellants. It is added to improve the elongation of the propellant at low temperatures and to improve processing properties such as lower viscosity for casting or longer pot life of the mixed but uncured propellants. So nitroglycerin is the plasticizer which is used in some of the propellants, which is also used as a fuel and which is also used to improve the elongation of propellants at low temperatures and to improve the processing properties of some of the propellants. Then we have additives. So even we have seen for liquid propellant rocket engines that additives are used. So some small amount of additives are used for many purposes, including accelerating or lengthening the curing time, that is to increase the curing time, or to improve the rheological properties, easier casting of viscous raw mixed propellants, improving the physical properties, limiting migration of chemical species from the propellant to the binder or vice versa. These are the properties which are improved after using some small amount of additives into the solid propellants. So this covers the solid propellant ingredients which are used for solid propellants for improvement of some of the properties and the performance as well. Next we will see some of the solid propellant hazards with this propellants. So with proper precautions and equipment, all common propellants can be manufactured, handled and fired safely. It is necessary to fully understand the hazards and the methods for preventing hazardous situations from arising. So each material has its own set of hazards and one has to be very careful when they are handling such propellants for any application. So we will see some of the hazards here. So first one is inadvertent ignition. So if a rocket motor is ignited and starts combustion when it is not expected to do so, the consequences can include very hot gases, local fires, or ignition of the adjacent rocket motors. So, and also exhaust cloud can be toxic and corrosive. So if an ignition happens when it was not expected to happen, then it may cause many several hazards. So when this kind of ignition can be arise, so there are some of the factors due to which this ignition can cause. So first one is stray or induced currents activate this kind of ignition. There might be some stray currents which are induced inside the system which will cause to activate the igniter. So for this, the safe and arm systems are used in rocket motors. Then electrostatic charging causes a spark or arc discharge, which will again cause ignition to happen at an unexpected time. Then fires can cause excessive heating of motor exterior, which can raise the propellant temperature above the igniter point. Then impact or bullet penetration or dropping the motor onto a hard surface can also cause the ignition, which may be a case of an accident. So for this reason, all propellant liners or insulators should have sufficient electric conductivity to prevent the buildup of an electrostatic charge. Also, viscoelastic propellants are excellent absorbers of vibration energy and can become locally hot when oscillated for extensive periods at a particular frequency. So this way we can maybe reduce such kind of ignitions happening at the unexpected times. Next we will see aging and the useful life. So the aging of propellant can be measured with test motors and propellant sample tests. If the loading during the life of the motor can be correctly anticipated, it is then possible to estimate and predict the useful shell or storage life of a rocket motor. So if we are able to anticipate the loading during the life of the motor, then it is very easy to estimate and predict the useful shelf life storage of a rocket motor. Because when reduction in physical properties caused by estimated thermal or mechanical load cycles has reduced the safety margin on the stresses and or strains to a danger point, the motor is no longer considered to be safe to ignite and operate. Once this age limit or its predicted weakened condition is reached and the motor has a high probability of failure. So as we have seen that the propellant is stored inside the case for a very long time, so there might be reduction in the physical properties which is not very good and it can cause failure. So the shelf life can usually be increased by increasing the physical strength of the propellant, for example by increasing the amount of the binder, then selecting chemically compatible stable ingredients with minimum long-term degradation, or by minimizing the vibration loads, temperature limits, or number of cycles that may be controlled by storage and transport environment. So this is about aging and useful life. Next, it is about the insensitive munitions. So in military operations, an accidental ignition, an unplanned operation, or an explosion of a rocket missile can cause several damage to equipment and injure or kill personnel. So this has to be avoided or minimized by making the motor design and propellants insensitive to a variety of energy stimuli. The worst scenario is a detonation of the propellant, releasing the explosive energy of all the propellant mass, and this scenario is to be avoided. So such kind of miniations has to be avoided and precautions has to be taken. So the missiles and its motors must undergo a series of prescribed tests to determine the resistance to inadvertent ignition with the most likely energy inputs during a possible battle situation. These all factors has to be taken care of when we are dealing with solid propellant. Next is about case overpressure and failure. The motor case will break or explode if the chamber pressure exceeds the case burst pressure. So if the pressure inside the combustion chamber exceeds the case burst pressure or the sustainable pressure of the case, then the motor completely it will break or explode. So the release of high pressure gas energy can cause an explosion. Motor pieces could be thrown out into the adjacent area. So this type of motor failure can be caused by one of the following reasons. So the grain it may be overaged or there is porous or severely cracked and or has major unbonded areas due to severe accumulated damage. Then there has been a significant chemical change in the propellant due to migration or low order chemical reaction. This can reduce the allowable physical properties, weakening the grain so that it will crack or cause unfavorable increase in the burning rate. So this may cause the detonation inside the combustion chamber and the motor may break into pieces. So the motor has not properly been manufactured can also be one of the reasons for the change in the chemical properties and the physical properties of the propellant which can cause the detonation. Next one is the toxicity. There's a large share of all rockets do not have significant toxicity problem. A number of propellant ingredients and a few of the plastics used in fiber reinforced cases can be dermatologically or respiratory toxins. So it is not that all the propellants are toxic, but the ingredients which we are using in processing the propellant can cause a toxicity problem. They and the mixed uncured propellant containing these materials have to be handled carefully to prevent operator exposure. Also, this is toxic, so the personnel who is handling the propellant should be given proper treatment and regular tests has to be carried out. This means using gloves, face shields, good ventilation, and with some high vapor pressure ingredients, gas masks. The finished or cured grain or motor is usually not toxic, but when it is burned, it may cause toxicity because of the exhaust gases and the smoky flame. So there are some of the safety rules which we have to carry forward. So the most effective way to control hazards and prevent accidents is to train personnel in the hazards of each propellant of concern and to teach them how to avoid hazardous condition, prevent accidents and how to recover from an accident. So this has to be trained to the personnel who is handling the propellant to avoid such kind of hazards, or to design the motors, facilities and the equipment to be safe. Or we can design the motors or the facilities in which the propellant has to be stored to be safe. To institute and enforce rigid safety rules during design, manufacture and operations. Also, we can define some of the safety rules, that is no smoking and no matches in areas where there are propellants or loaded motors. Wearing spark-proof shoes and using spark-proof tools when handling the propellant. Shielding all electrical equipment to avoid the inadvertent ignition. Providing a water deluge, fire extinguishing system and test facilities to cool motors or extinguish burning. Proper grounding of all electrical equipment and items that could build up static electrical charges. So if we follow all these precautions and the rules, then it will be easy to handle the propellants and to avoid the hazards which are prone with the propellant. So the next topic we will see is propellant grain and grain configuration. So the grain is the shaped mass of the processed solid propellant inside the rocket motor. The propellant material and geometrical configuration of the grain determine the motor performance characteristics. Once ignited, it will burn on all its exposed surfaces to form hot gases that are then exhausted through a nozzle. So we have seen that the propellant grain is the charge which is stored inside the solid propellant combustion chamber. A few rocket motors have more than one grain inside a single case or chamber, and very few grains have segments made of different propellant compositions, which allows different burning rates. So there are some definitions and terminologies which is important when we are dealing with grains. So first, that is configuration, that is the shape or geometry of the initial burning surfaces of a grain as it is intended to operate in a motor. Cylindrical grain is a grain in which the internal cross section is constant along the axis regardless of the perforation shape. The neutral burning is motor burn time, during which thrust, pressure and burning surface area remain approximately constant, typically within about plus minus 15%. Sleever is nothing but unburnt propellant remaining or lost that is expelled through the nozzle. Then progressive burning is burn time during which thrust, pressure and burning surface area increase. Regressive burning is the burn time during which thrust, pressure and burning surface area decrease. So these are some certain definitions and terminologies. Then perforation is the central cavity port or flow passage of a propellant grain. Its cross section may be cylinder, a starch. Then action time is the burning time plus most of the time to burn slivers, typically the interval between the initial and final 10% of pressure points on pressure time trace. Deflagration limit is the minimum pressure at which combustion can still be barely self-sustained and maintained without adding energy. Below this pressure, the combustion gases altogether or may be erratic and unsteady, with the tube appearing and disappearing periodically. Then inhibitor is a layer or coating of slow or non-burning material, usually a polymeric rubber type with filler materials, applied, which may be glued, painted, tipped or sprayed to a part of the grain's propellant surface to prevent burning on that surface. So this is inhibitor, which is nothing but a layer or coating of slow or non-burning material. Then there is liner, that is a sticky non-self-burning thin layer of polymeric type material that is applied to the cases prior to casting the propellant in order to promote good bonding between the propellant and the case or the insulator. Then last one, that is internal insulator, that is an internal layer between the case and the propellant grain made of an adhesive thermally insulating material that will not burn readily. Its purpose is to limit the heat transfer to and the temperature rise of the case during the rocket operation. These are the different definitions and terminologies involved with propellant grain. And here we can see one graph which describes the three types of burning, that is neutral, progressive and regressive. So we can clearly see that for progressive, with the time the burning rate or the pressure is increasing. For neutral it is remaining constant, and for regressive it starts to reduce after some time. Then we will see different configurations for propellant grain. The geometry is crucial in grain design. For a neutral burning grain, approximately constant thrust, for example, the burning surface has to stay approximately constant, and for a regressive grain, the burning area will diminish during the burning. So here we can see different configurations to the left figure. That is, first one is the end burner, in this case bonded, and it will burn neutrally. Burn area is constant, that is no perforation is given here. Then the next one is internal burning tube. with the progressive burning is having a single slot in between. Then there is slots and tube which will give us neutral burn. Then we have several configurations of star, wagon wheel, etc. The effects of propellant burning on surface area is readily apparent for simple geometric shapes such as rods, tubes, wedges, and slots. Certain other basic surface shapes burn as follows, that is, external burning rod will give us regressive burning, external burning wedge will also give us regressive burn. So to avoid this, most propellant grains combine two or more of these basic surfaces to obtain the desired burning characteristics. That is, the star perforation, for example, combines the wedge and the internal burning tube. So these are various grain configurations which are being used today also. End burning grain, that is burning like a cigarette, is unique. It burns solely in the axial direction and maximizes the amount of propellant that can be placed in a given cylindrical motor case. In large motors, that is over 0.6 meter diameter, these end burners show a progressive thrust curve. The trend has been to discontinue configurations that give weak grains which can form cracks, produce high sliver issues, have a low volumetric loading fraction, or are expensive to manufacture. So the current designs concentrate on relatively few configurations. The figure indicates typically single grains with combination of two basic shapes. The term conical is the contraction of the words cone and cylinder. So here we can see three different types of configurations for the grain which are used in today's designs. There are two methods of holding the grain in the case. So first one is cartridge loaded or freestanding grains. So they are manufactured separately from the case, that is by extrusion or by casting into a cylindrical mold or cartridge and then loaded into or assembled into the case. Freestanding grains can more easily be replaced if the propellant grain has aged excessively. They are used in some small tactical missiles and a few medium-sized motors, and they often have a lower cost and are easier to inspect. In this kind of installation, the grain is made separately and the case is made separately, and when they are about to be used, the grain has to be assembled inside this case. So that's why it is called as freestanding grains. Then the next category is case bonded grains. So here the case is used as a mold and the propellant is cast directly into the case and is bonded to the case or the case insulation. They give somewhat better performance, a little less inert mass because there are no holding device, support pad, and less insulation, a better volumetric loading fraction, but are more highly stressed and often somewhat more difficult and expensive to manufacture. So today almost all larger motors and many tactical missiles motors use case bonding kind of installation. So in case bonding type, the case itself is used as the mold and the propellant is directly casted inside it. So the advantage is that it will have a little less inert mass, that is no holding device or support pads, and less insulation as it was required into the freestanding grain. But again they are more highly stressed and somewhat more difficult and expensive to manufacture. So this covers everything about the solid propellants and propellant grain and its configurations. Now we will move on to the combustion process which is involved in solid rocket motors. So the solid propellant ignition consists of a series of complex rapid events, so which will start on receipt of a signal that is usually electric and includes heat generation, that is the igniter part, then transfer of heat from the igniter to the motor grain surface, spreading the flame over the entire burning surface, filling the chamber free volume cavity with the gas, then elevating the chamber pressure without serious abnormalities. So these are the rapid events which happen inside the combustion chamber when the igniter is ignited and the combustion initiates. So the energy released in a combustion is between 95 and 99.5% of the possible maximum, and this is difficult to improve. The rocket motor designers have been concerned not so much with the burning process as with the controlling the combustion, because it involves start, stop, heat effects, and various other parameters, and with preventing the occurrences of combustion instabilities also. So the igniter in a solid rocket motor generates the heat and gas required for the motor ignition. Conventionally, the ignition process is divided into three phases for analytical purposes. So for simplicity, the ignition process has been classified into the three phases. That is, first phase, ignition time lag. It covers the period from the moment the igniter receives a signal until the first surface grain burns. Then phase 2, that is flame spreading interval. The time from first ignition of the grain surface until the complete grain burning area has been ignited. And the last one, that is phase 3, chamber filling interval. the time for completing the chamber filling process, and for reaching equilibrium chamber pressure and flow. So this phase ignition process has been divided for three phases. That is the time interval in which this igniter works, is receiving from the first signal and igniting of the first burning grain till the equilibrium chamber pressure has been reached. This is the graph which perfectly defines the three phases. So with the first phase, we can see in how much milliseconds this happens and how much the motor chamber pressure increase along with the ignition pressure. Then for phase 2, the motor chamber pressure increases and slowly the igniter pressure starts to reduce. Along the third phase, the equilibrium for chamber pressure has achieved while the ignition pressure is getting reduced. So the ignition will be successful once enough grain surface is ignited and burning so that the motor will continue to raise its own pressure to the operating chamber pressure. Then the critical process seems to be a gas phase reaction above the burning surface when propellant vapors or decomposition products interact with each other and with the igniter gas products. If the igniter is not powerful enough, some grain surfaces may burn for a short time, but the flame will be extinguished. So these are some of the ignition properties or ignition process details for a solid rocket motor. So the satisfactory attainment of equilibrium chamber pressure with full gas flow is dependent on some of the factors. So first factor is that characteristics of the igniter and the gas temperature, composition and flow issuing from the igniter. So for any igniter, the ignition can be called as successful when the equilibrium chamber pressure is achieved with full gas flow inside the combustion chamber. So to attain this satisfactory attainment, there are certain factors like characteristics of the igniter and the gas temperature, composition and flow issuing from the igniter, motor propellant composition and grain surface ignitability, heat transfer characteristics by radiation and convection between the igniter gas and grain surface, grain flame spreading rate, the dynamics of filling the motor free volume with hot gas. So these are the some dependent factors for equilibrium chamber pressure with full gas. Again, the ignitability of a propellant is affected by many other factors like propellant formulation, initial temperature of the propellant grain surface, surrounding pressure, mode of heat transfer, grain surface roughness, age of the propellant, composition and hot solid particle content of the igniter gases, igniter propellant and its initial temperature, velocity of the hot igniter gases relative to the grain surface, and the cavity volume and the configuration used for solid rocket motors. So, if any of the following factors have a significant impact on the ignition, then the equilibrium chamber pressure won't be achieved, and there will be some abnormalities which will cause combustion instability. So one has to be very familiar with all the factors which affect the ignitability of a propellant and has to take care of such factors to avoid them with using some solid propellant ingredients which we have discussed earlier. Then moving on to the extinction on thrust termination. So sometimes it is necessary to stop or extinguish the burning of a solid propellant motor before all the propellant has been consumed. Because when a flight vehicle has reached the desired flight velocity, say for a ballistic missile to attain a predetermined velocity or for a satellite to achieve an accurate orbit or a precise tool impulse cutoff is needed. Also it is needed as a safety measure when it appears that a flight test vehicle will unexpectedly fly out of the safe boundaries of a flight test range facility, or to avoid collisions of stages during a stage separation maneuver requiring a thrust reversal for multi-stage vehicles, or during research and development testing when one wants to examine a partially burned motor. So when such factors are present, then a thrust termination or extinction is useful or needed. But for solid propellants, it is very difficult to achieve this stage because once ignited, the grain will consume itself completely by burning at a predetermined rate. But there are some of the processes by which we can attain this thrust termination. So first one is very rapid depressurization. So usually by a sudden large increase of the nozzle throat area or by fast opening of additional gas escape areas or ports, this very rapid depressurization can be achieved. The most common technique neutralizes the thrust or reverses the net thrust direction by suddenly opening exhaust ports in the forward end of the motor case. So this depressurization can be achieved by opening some of the ports which are present in the forward direction of the motor case, And such a thrust reversal using ports located on the forward bulkhead of the case is achieved in the upper stages of Nimittaman and Poseidon missiles. So this kind of rapid repressurization has been also tested on some of the missiles and which has been successful. So this way we can terminate the thrust in between by using a depressurization system. Also there are some other methods like during some motor development projects it can be helpful to see a partially consumed grain. The motor operation is stopped when the flames are quenched by an inhibiting liquid such as water. References had showed that adding a detergent to the water allows better contact with the burning surface and reduces the amount of water needed for quench. So we can even use quenching method by using water to stop the propellant grain burning in development projects only, not in the actual rocket motors which are very huge and which are used for space shuttle or the actual rocket engines. Then lowering the combustion pressure before the pressure deflagration limit can also be one of the process which we can go for. So compared to very rapid depressurization, this depressurization occurs quite slowly. Many solid propellants have a low pressure combustion limit of around say 0.05 to 0.15 MPa. This means that some propellants will not extinguish when vented during a static sea level test at 1 atm, that is at 1 MPa, but will stop burning if vented at high altitude. We can also reduce the combustion pressure below the pressure deflagration limit for the propellants which are used for development projects. But the same we cannot use at the high altitudes because again if you lower the combustion pressure inside the combustion chamber then the flame may extinguish. A sudden depressurization is effective because the primary combustion zone at the propellant surface has a time lag compared to the gaseous combustion zone, which at the lower pressure quickly adjusts to a lower reaction rate and moves farther away from the burning surface. So compared to the other techniques which are given here, the rapid depressurization is the technique which one can go for because the gases created by the vaporization and pyrolysis of the hot solid propellant cannot all be consumed in a gas reaction close to the surface and some will not burn completely. As a result, the heat transfer to the propellant surface will be quickly reduced by several orders of magnitude and the reaction at the propellant surface will diminish and stop. Experimental results show that a higher initial combustion pressure requires a faster depressurization rate to achieve extinction. This way we can achieve this thrust termination for solid propellant rocket at the development stages or at the high altitude stages using rapid depressurization. Next we will discuss about combustion instability. There are fundamental differences with liquid propellant combustion behavior. In liquid propellant there is a fixed chamber geometry with a rigid wall, liquids and fed systems and injectors that are not part of the oscillating gas in the combustion chamber and can interact strongly with the pressure oscillations. In solid propellant motors, the geometry of the oscillating cavity increases in size as burning proceeds and there are stronger damping factors such as solid particles and energy absorbing viscoelastic materials. In general, combustion instability problems do not occur frequently or in every motor development, and when they do occur, it is rarely the cause for a drastic sudden motor failure or disintegration. So for solid propellant motors, there are basically two types of combustion instabilities. So the first one that is acoustic oscillations and next one which is vortex shedding phenomenon. So the set of acoustic resonances or pressure oscillations can occur with any rocket motor, but the vortex shedding phenomenon can occur only with relatively large segmented grains or in grains with circular slots. So first we will discuss about acoustic instabilities. So undesirable oscillations in the combustion cavity propellant rocket motors is a continuing problem in the design, development, production and even long-term retention of solid rocket motors. So the cavity which is present inside the propellant grain, there are undesirable oscillations in this cavity which has been the problem from the design, development and production age for the solid propellant rocket motors. While acoustically softer than a liquid rocket combustion chamber, the combustion cavity of a solid propellant rocket is still a low loss acoustical cavity containing a very large acoustical energy source, the combustion process itself. So a small fraction of the energy released by the combustion is more than sufficient to drive pressure vibrations to an unacceptable level. Combustion instability can occur spontaneously, often at some particular time during the motor burn period, and the phenomenon is usually repeatable in identical motors. So these acoustical instabilities are mostly caused inside this cavity which is present inside the propellant grain, and a single release of energy inside this cavity can cause a very harmful danger for the rocket motor. Both longitudinal and transverse waves, radial and tangential, can occur for this acoustic instability. In figure also we can see simplified diagram showing two periods of combustion instabilities in the pressure time history with enlargements of the two sections of this curve. The pressure oscillations increase in magnitude and the thrust and burning rate also increase along with this. Then the frequency seems to be function of the cavity geometry, propellant composition, pressure and internal flame field. So if we vary these factors, then we may be able to control the frequency of this oscillation. As the internal grain cavity is enlarged and local velocities change, the oscillations often abates and disappears. The same may not happen for each grain. The time and severity of the combustion vibration tend to change with the ambient grain temperature prior to motor operation. Figure here shows two instances where a combustion instability was triggered and its amplitude increased for a brief period and then diminished. Frequency decreased because of the cavity volume increase and then the instability has been disappeared. Nevertheless, the resulting thrust time curve is different and the flight path will be changed, often preventing the reaching of a mission target. So this combustion instability can cause change in the thrust time curve and also the flight path, which may prevent reaching to the mission target which was designed for the rocket. Next, moving to the next instability, that is vortex shedding instability. This instability is associated with burning on the inner surfaces of slots in the grain. Large segmented rocket motors have slots between segments, and some grain configurations have slots that intersect the center line of the grain. So the figure here shows that hot gases from the burning slot surfaces enter the main flow in the perforation or central cavity of the grain and then turn into a direction towards the nozzle. The flow from the side streams restrict the flow emanating from the upstream side of the perforation and in effect reduces the port area. This restriction causes the upstream port pressure to rise. Sometimes there is substantial pressure rise. The interaction of the two subsonic gas flows causes turbulence. Vortices form and are periodically shed or allowed to flow downstream, thereby causing an unstable flow pattern. The vortex shading pattern can interact with the acoustic instabilities also. So the remedy usually is to apply inhibitors to some burning surfaces or to change the grain geometry. For example, by increasing the width of the slot, the local velocities are reduced and the vortices become less pronounced. So the inhibitors which we discussed earlier, which are non-burning materials, so those inhibitors can be used at some burning surfaces or some grain geometries can be changed by increasing the width of the slot. So these are the two combustion instabilities which are present for solid propellant rocket engines. Now we will see how we can assess these instabilities and provide remedies and design changes. So in contrast with liquid rocket technology, an accepted combustion stability rating procedure does not now exist for full-scale rocket motors. Undertaking stability tests on large full-scale light hardware rocket motors is expensive and therefore lower cost methods such as subscale motors, e-burners and other test equipments have been used to assess motor stability. The best known and most widely used method of gaining combustion stability related data is the use of a T-burner, an indirect limited method that does not use a full-scale motor. So in figure also we can see a sketch of a standard T-burner. It has a 1.5-inch internal diameter, double-ended cylindrical burner vented at its midpoint. Venting can be through a sonic nozzle to the atmosphere or by a pipe connected to a surge tank which maintains a constant level of pressure in the burner cavity. T-burner design and usage usually concentrate on the portion of the frequency spectrum dealing with the transverse oscillations expected in a full-scale motor. The desired acoustical frequency to be imposed on the propellant charge as it burns determines the burner length, that is distance between closed ends. The nozzle location midway between the ends of the T-burner minimizes attenuation of fundamental longitudinal mode oscillations in the propellant grain cavity. Use of the T-burner for assessing the stability of a full-scale solid rocket presupposes valid theoretical model of the phenomena occurring in both the T-burner and the actual rocket motor. These theories are still not fully validated. These are just some of the research have given the idea of this use of T-burner, but still they are not fully validated. Then the next thing that once an instability has been observed or predicted in a given motor, the designer has to fix the problem. There is no sure method for selecting the remedy and none of the cures suggested below may work. The usual alternatives we can go for are here. First one, that is changing the grain geometry to shift the frequencies away from the undesirable values. Sometimes changing fin locations, post cross-section profile or member of slots has been successful. This way we can follow and change the geometry and assess the instabilities, or changing the propellant combination. Using aluminium as an additive has been most effective in curing transfer instabilities, provided that the particle size distribution of the aluminium oxide is favorable to optimum damping at the distributed frequency. Also, changing size distributions and using other particulates, that is zirconium or Al2O3 or carbon particles, has been effective in some cases. Sometimes changes in the binder have also worked. And the third one, that is adding a mechanical device for attenuating the unsteady gas motions or changing the natural frequency of the cavities. Various inert resonance rods, baffles, or paddles have been added, mostly as a fix to an existing motor with observed instability. They can change the resonance frequencies of cavity but introduce additional viscous surfaces losses and cause extra inert mass and potential problems with heat transfer or erosion. So once the instability has occurred and have to fix the problem, we can go for such remedies to tackle the instability. We can also address this combustion instability in design process, usually through a combination of some mathematical simulation, understanding similar problems in other motors, studies of possible changes, and supporting experimental work. While example which we saw, T-burner measuring particles, size distributions, etc. So implementing this in design process itself, we can address the instability and deal with it. Most solid propellant rocket companies have in-house 2 and 3-dimensional computer programs to calculate the likely acoustic modes, maybe axial, tangential, radial, and combination of this for a given grain motor. The initial and intermediate cavity geometries and the combustion gas properties calculated from thermochemical analysis. Development is happening to address and to understand these instabilities using numerical and analytical approaches. So some of the major companies, they have in-house 2 and 3-dimensional computer programs to calculate this likely acoustic modes. So data on combustion response, dynamic burn rate behavior, and damping can be obtained from the T-burner tests. Data on particle sizes can be estimated from the prior experience, observation through windows or plane measurements. Because combustion response is useful and T-burners can help us to obtain the damping, and also particle size data can also be estimated from prior experience. Estimates of nozzle loss, friction, or other damping needs to be included when we are in the design process of solid propellant rocket engines. Depending on the balance between the gain and damping, it may be possible to arrive at conclusions on the grain's propensity to instability for each specific instability mode that is analyzed. So there is always a trade-off between the amount of work spent on the expensive analysis, subscale experiments, and computer programs which will not always guarantee a stable motor, and taking a chance that a retrofit will be needed after full-scale motors have been tested. If the instability is not discovered until after the motor is in production, it is usually more difficult, time-consuming, and expensive to fix the problem. So these instabilities has to be addressed in the design process, should have made proper changes. Range geometry or tests have to be done using T-burners, and particle size data has to be estimated in the design process itself. Also, there is one more way by analysis and simulation. So using computers, it has been possible to successfully simulate the combustion for some limited cases, such as for validating or extrapolating experimental results or making limited predictions of the stability of motor designs. This applies to well-characterized propellants where empirical constants such as propellant response or particle size distribution have been determined and where the range of operating parameters, internal geometries, or sizes has been narrowed. Then it is likely that a reliable, simple analysis will be found for predicting the occurrence, severity, nature, and location of instability for a given propellant and motor design. The physical and chemical phenomena are complex, multidimensional, unsteady, non-linear, influenced by many variables, and difficult to emulate mathematically without a good number of simplifying assumptions. However, the theoretical analysis gives insight in the physical phenomenon can be a valuable contributor to solving instability problem and has been used for preliminary design evaluation of grain cavities. Then computational fluid dynamics has taken the role of developing a full-scale model for simulation of such complex combustions for liquid propellant rocket engines as well as for solid propellant rocket engines. Moving on to the last part of this topic, that is propellant processing and manufacture, we will see some of the processing and manufacturing techniques for propellants. The manufacture of solid propellant involves complex physical and chemical processes. Earlier, it was produced by several different processes, including the compaction or pressing of powdered charges, extrusion of propellant through dies under pressure using heavy presses, and mixing with a solvent which were later evaporated. The rheological properties of the uncured propellant, meaning its flow properties in terms of shear rate, stress, and time, are all important to the processability of the propellant, and these properties usually change substantially throughout the length of the processing line. An important objective in processing is to produce a propellant grain-free of cracks, low-density areas, voids, or other flaws. In general, voids and other flaws degrade the ballistic and mechanical properties of the propellant grain. Finely dispersed gas in a propellant grain may result in an abnormal high burning rate, one so high as to cause catastrophic motor failure. Special process equipment is needed in manufacturing of the propellant. So the main objective while processing any propellant is to produce a propellant grain free of cracks, low density areas, voids or other flaws, because these flaws or voids will degrade the ballistic mechanical properties of the propellant grain, which may cause abnormally high burning rates so that motor catastrophic failure can also occur. So we will see processing and manufacturing of composite propellants first. So the mixing and casting processes are the most complex and are the most critical than other processes in determining the quality, performance, burn rate, and physical properties of the resulting propellant. Batch type processing of propellant, including the casting, that is pouring of propellants into motors that serve as their own molds, is the most common method. So this casting method has been used for composite propellants. For very large motors, several days are needed for casting perhaps 40 batches into a single case, forming a single grain. Vacuum is always imposed on the propellant during the mixing and casting operations to remove air and other dispersed gases and to avoid air bubbles in the grain. Viscosity measurements of mixed propellants are made for quality control. Time is important in terms of pot life. That period of time the uncured propellant remains reasonably fluid after mixing before it cures and hardens. Short pot life, that is a few hours, requires fast operations in emptying mixers, measuring for quality control, transporting and casting into motors. So this is the manufacturing process or the processing method for composite propellants, where how they are casted into the molds. Vacuum is always present and viscosity measurements have been taken care of. The manufacturing equipment includes mechanical mixers, usually with 2 or 3 blades rotating on vertical shafts, agitating propellant ingredients in a mixer bowl under vacuum. Then casting equipment, curing ovens or machines for automatically applying the liner or insulator to the case. This is the complete process, including the mechanical equipments for composite propellants. Next, we will see the processing and manufacturing of double-based and modified double-based propellants. Double-based propellants are manufactured by a different set of processes than composite propellants. The key is the diffusion of the liquid nitroglycerine into the fibrous solid matrix of nitrocellulose, thus forming by means of solvation a fairly homogeneous, well-dispersed, relatively strong solid material. Several processes for making double-based rocket propellant are in use today, including extrusion and slurry casting. In the slurry casting process, the case or the mold is filled with the solid casting powder, a series of small solid pellets of nitrocellulose with a small amount of nitroglycerine, and the case is then flooded with liquid nitroglycerine, which then solvates the pellets. Double base processing requires equipment for mechanically working the propellant, that is rollers or presses, or special tooling for allowing a slurry cast process. Computer-aided filament winding machines are used for layering the fibers of fiber-reinforced plastic cases and nozzles. So mostly slurry casting and extrusion is used for double base and modified double base propellants. Next we will see post-manufacturing of grains, what all tests are carried out. So the finished grain or motor is usually inspected for defects, cracks, voids and debonds using X-rays, ultrasonic, heat conductivity or other non-destructive inspection techniques. A determination of the sensitivity of motor performance, including possible failure to propellant voids and other flaws, often requires the test firing of motors with known defects. Samples of propellants are taken from each batch, tested for rheological properties, and cast into physical property specimens and or small motors which are cured and subsequently tested. Data from the tests are important in establishing inspection criteria for accepting and rejecting production motors. So once the grain is manufactured, several tests are carried out like X-rays, ultrasonic, heat conductivity or other non-destructive tests to find cracks, voids and debonds. To check the rheological properties, the propellant samples are being taken out from each batch and they are checked for their physical property using specimens. To determine the sensitivity of the motor performance and also include possible failure, the propellant voids and other flaws often require the test firing of motors with known defects. These tests give us data which will be useful for the criteria for accepting and rejecting the production motors. So these are the post-inspection tests which are carried out for propellant grains once they are produced. So this covers the propellant processing and manufacturing of the solid propellants. So the summary for today's class is that first we have seen fundamentals of solid propellant rocket motors, that is their processes, various components, advantages, disadvantages of using them, various applications based on several factors, and classification based on many categories. Then next we have discussed different types of solid propellants with their features, like some examples, subclasses, advantages and disadvantages, in which briefly we have discussed about double base propellants and composite propellants. Next we saw various desirable physical properties of solid propellants, that it should have high density, low absorption of moisture, long life, simple, reproducible, safe, low cost, non-toxic, etc. Then we have seen different propellant hazards, their features, techniques to avoid them, precautions one has to take care of, that is inadvertent ignition and sensitive munitions, case overpressure and failure, toxicity, etc. Safety rules, like we have to use masks, we have face shields, and water extinguishing has always provided in the testing and processing areas. Then we saw variety of propellant grains and their configurations, applications, several related definitions, and different types or methods of holding the propellant in the case. That is, we saw case bonding and freestanding grain installation designs for solid propellants. Then we have seen different grain configurations like end burning grain, progressive grain, regressive grain. Then we discussed complex combustion process of solid propellants, different phases of ignition, chamber pressure importance, factors which affect the satisfactory attainment of chamber pressure equilibrium, and variety of factors affecting the ignitability of propellants. Then we discussed about importance of thrust termination in solid propellants, the various processes to attain it, that is rapid depressurization, flame quenching with water, lowering the combustion pressure below the flame deflagration limit, and we saw that rapid depressurization is most suitable method to attain the thrust termination for development projects as well as when the rocket is flying at high altitudes. Then we saw two combustion instabilities occurring in solid propellants, its features, occurrence, that is acoustic and vortex shading instabilities we saw in detail. Then combustion stability assessment, remedy, design aspects of solid propellants we have seen, that is how we can use deburners and we can get data. Then various other techniques to control the instability and design changes to do so, that is we can even change the grain design to fix the instability problem. Then we have discussed various analysis and simulation techniques to use to understand and predict the instability before going to a full-fledged model of solid propellant rocket motor. Then we saw propellant processing and manufacturing techniques for double base and composite propellants. That is, composite propellants they use casting process, and double base propellants they use extrusion and slurry casting processes for their manufacturing. Then lastly, we have seen various inspection tests carried out once the solid propellant is ready, that is X-rays, ultrasonic, heat conductivity and other entity tests are carried out, and the data are used as a criteria for accepting and rejecting the propellants once they are produced. So this covers the solid propellant rocket engines topic, and these are the references for today's class. In next class we will start with thrust chambers. Thank you.